Hey class, this is the second video of our ionic bonding chapter, and this is going to be talking about ionic compounds containing transition metals. Those metals located within groups 3 to 12 on the periodic table. Things like cobalt, chromium, copper, iron, manganese, and so forth. The difference between these and regular metals is that you have to specify what their oxidation number is. Because sometimes iron likes to be a 2+. Sometimes iron likes to be a 3+, and there's no way to predict that. We have to be told what the oxidation number is in order to correctly write the formula. So how it's going to be told to you is through Roman numerals. Lead 4, chromium 3. Remember, it's always a positive ion, so lead 4 is lead 4+. Chromium 3 is chromium 3+. And just a reminder, in case you've forgotten your Roman numerals, you only need to know through 4 for this particular part. You won't see any Roman numerals bigger than 4 when it comes to transition metal bonding. So instead of just saying sodium ion, you have to say lead 4 ion, chromium 3 ion, and so forth. Let's look at some examples of how that would work out. All right, first one, copper 2 sulfide. Copper, write down its symbol, just like before, Cu. Don't put Co for copper. Remember, copper is see you later copper. And then it tells us it's a 2+. 2+. And then sulfide, we've got sulfur, and sulfur's in group 6 where it needs 2 electrons. 2-. Now the process is exactly the same. You want to crisscross applesauce and then write your correct formula. 2 goes there, 2 goes there. You end up with Cu2S2. But like I said last time, all you need is Cus. You can reduce those 2's down to 1's. Okay, let's look at copper as a 1+ ion. Copper 1 would be Cu1+. And then oxygen is always a 2-. It's in group 6. Crisscross applesauce. We end up with Cu2O1. Cu2O. Okay, let's look at chromium 3 nitride. Chromium symbol is Cr. It tells us it's a 3+. Nitrogen symbol is just N. It's in group 5, so it needs to gain 3 electrons. 3-. Crisscross applesauce. Anybody see what's happening here? 3 and 3. That's going to reduce down to 1 and 1. Cr, N. Okay, let's look at 2 exceptions to the rule. There's always exceptions. Silver being one of them. Silver is always a +1 ion. So silver does not have to be specified. Zinc is always a +2. So for zinc or silver, we do not have to specify in parentheses what the oxidation number is. So just like before, silver bromide. Let's write the symbol for both. AgBr. We know silver is going to be a 1+. Bromine's in group 7, almost there. It just needs 1 electron. So when it gains 1, it's going to become a -1. Crisscross applesauce, we end up with AgBr. And then for zinc fluoride, again, not specified because we always know zinc is a +2. Fluorine is in the same group as bromine, so it just needs 1 electron. Crisscross applesauce, you end up with zinc 1, F2. So just like binary compounds, except they give us the charge or the oxidation number for the metal. Let's look at naming them. Naming them can be a little bit more tricky. All right. So this first one is FeCl2. The steps for doing this, we have to name the metal, iron, leave a space, name the non-metal but change the ending, iron chloride. Now, to figure out the oxidation number, you have to do a little work. So, first off, we have to see what chlorine's charge is. Chlorine is a -1. If there's 2 chlorines at a -1 charge, our anion charge total is going to be -2, which means our cation charge total has to be +2. We only have 1 iron to do so, so we know this iron has to be a +2. And we put that in parentheses. Now, one little trick you can get away with most of the time is to look at the subscript of the anion. That's generally going to match up to your charge for your cation, but not 100% of the time. So we can say iron 2 chloride. And for these next examples, I'm going to change it up just a little bit. And let's see here. All right, look at this next one. AgN. Ag is silver. N is nitrogen, but leave a space. And we're going to say nitride. Now, this would technically have to be Ag3N because nitrogen is a -3. But we know silver is always +1. Now, do we have to write the +1? No, but it's not incorrect if we do. For this practice, we'll go ahead and write it. Okay, look at this one, CuCl3. See you later, copper. Leave a space. Cl is chlorine, but we're going to change it to chloride. And then 2 ways of looking at it. Chlorine is a -1. We have 3 of them. That's a -3. Total charge for the anion, we need a +3. Total charge for the cation. We only have one element to do so, one atom, excuse me. So copper would have to be a 3+ in this scenario. Now, we could have gotten away with it again on our little trick. If you just look at the subscript of the anion, that will tell you the charge of the cation most of the time. So copper 3 chloride. Copper 3 chloride. Okay, look at this last one. Hg2O. Almost water, but with a little G added. Mercury is what Hg is. Leave a space. Oxygen becomes oxide. Now, O doesn't have a subscript, or does it? It does. Technically, that's a 1. So let's skip to the end and see if that works. Hg1. So mercury 1 oxide. Now go back and look and see if that balances out. Oxygen, you know, is a -2, and there's 1 atom, so the total charge on this side for the anion is -2. This side's got to be +2. And in this case, you have 2 atoms of mercury to make that +2 charge. 2 divided by 2 gives us 1. So our method worked again. Mercury 1 oxide. We're not going to get super involved with transition metals because they don't work, they don't function as well as our representative class does. But we will have to know how to name and formulate these for our test and moving forward. Next up will be the polyatomics.